A text problem gave us a velocity versus clock time graph for a car where the clock time is 1, 2, 3, 4, 5, 6, 7, 8 hours. So the clock time is marked off in hours and the speed in miles per hour. What we want to do is we want to see what the position of the car is at the end of each hour. We want to see how the position of the car changes. So we can make more or less a trapezoidal approximation to the area under this graph. We're not restricted to a trapezoidal approximation though. We can make any reasonable estimate we can. So what we're going to do is we're going to make an estimate on each interval of the distance that the car travels. Each interval has a width of an hour, so the distance is just going to be equal in number to the average speed of the car over the interval. Now on this first interval it appears that the car goes from 0 to about 55 miles per hour. In your text you have a grid on such a graph and you can make a fairly accurate estimate. So we're going to assume that the car goes from 0 to 55 miles an hour. That would be an average of 27.5 miles an hour, so the car would go 27.5 miles. The curve isn't exactly a straight line here. A trapezoid would be a straight line. So taking a few liberties, we're going to estimate that the distance is a little over 27.5 miles or 30 miles. On the second interval, well, the speed goes from 55 to 72. The average between 55 and 72, I believe, would be 60, what's the difference here? 55 to 72, 17, yeah, 63.5 miles an hour. But the curve is obviously a little bit rounded at the top, so the trapezoid would underestimate that, so we're going to round that off and say 65 miles. And making similar estimates on the different areas, we see that the car should travel these distances in the various hours. Now I don't know who would drive a car like that, taking 2 hours to accelerate up to 72 miles an hour and then 6 more hours to slow down to a rest. I'm not sure what they're doing, but that's not a very realistic curve. However, it makes a good problem if we simply don't question where it came from and accept it. Now there's more to the problem, but let's just see what we get. For the car's position, at clock time t equals 1, we will have gone 30 miles. At clock time t equals 2, we'll have gone 30 and 65 or 95 miles. The next interval we move 70 miles, as you can see. So we will have gone a total of 165 miles. Another 62 puts us up to 227 miles, and so on. This gives us the position of the car versus clock time. Okay, and the etc. indicates that we can continue doing this until we run out of data. Now there's a hypothesis in the problem that a truck starts out at the same time moving at 50 miles every hour. Well, we don't have to do a graph to see how far the truck has traveled by the end of each hour. It's going to go 50, 100, 150, 200 miles by the end of the first, second, and third hours. We notice that the truck is ahead of the car after the first hour, a little bit ahead of the car after the second hour. It's behind the car after the third and the fourth hours. Maybe later on, as a matter of fact, almost certainly as the car slows down, the truck will again overtake the car.